I know, laughably short amount of time. So I know that we're going to kind of go through some slides and you're going to record this. But I do really want to hear from folks have questions. So we also have a document where many of you put in questions. I tried to annotate that document where those you might find answers in these slides, and everyone should have or will have available to them these slides, so you'll have them. But at the end, if I've missed anything or whatever, please let's have an open Q&A. Thanks for everyone who are able to from time to time or very often show up for those second now Friday meetings, where we try to kind of go through stock assessments. And so some of the stuff you will probably been exposed to before, but repetition is not a bad thing. And for those of you who are new to this, yeah, don't hesitate asking any questions you might have. And it's great to be with both the GAP and the GMT with this. So let's just start right off. Let's talk about the basics of stock assessment. Let's talk about the box that is the stock assessment model. What is that? Let's just break it down really simply. Well, we think simply, right? Because let's break those words down. Stock is a some sort of collection of fish population, which is a loaded word, and we have a whole thing that we're going to do trying to define stocks. Let's just assume that we've defined the stock, and the assessment part is basically a measure of its health. How is it? And given what we would like to do, how much risk is there applied to the health of the stock? So stock assessments are a tool using evidence, data, insight to help us understand the health of the fish population, because we do have objectives. We want a sustainable stock so we can have access to it into the future. And these assessments will hopefully drive our ability to support management decisions. So we have this. We'll get back to what that box actually is doing here in a second, but say you put some information into that box and it spits out some sort of output. And usually, again, it's going to be measuring some level of health of the population, and ultimately it's going to help us determine how much we can catch. Now, our models, those boxes of stock assessments, are always going to be some level of an abstraction of reality, because we cannot measure every single thing, every sort of reality, and put it into a model. By definition, a model is a reduction from absolute knowledge to some sort of approximation of reality that is useful to us. It's a picture of Picasso's bowls, and even in that bottom middle one where there's barely a drawing, you can kind of tell there's some sort of four-legged creature there, right? And that's sometimes what our models look like. They're very heavy on a little sketch of reality, less on the data. We'll get to that in a second. But when we apply models, we need to understand how we might be simplifying reality, and therefore what assumptions we're making. And we also need to understand how different models are set up, what we call model specifications. I'll come back to that here in a second. And how the specifications drive the output of the model. So let's get into one of our very first really important concepts here, is that when we are setting up some sort of vision of reality that is not exactly reality, we are going to have a bit of a trade-off. We're going to have a trade-off between what we assume to be real and then the measured parts, the data that we're putting into the model. We would like to have more data. And when I say more data, I'm not just saying more numbers of things to put in, because sometimes we have a lot of things we can put into the model that really don't tell us anything, and we'll deal with that here a little bit later. But we'd like to have more informative data, therefore avoiding having to make so many assumptions about the stock. So we kind of have a bit of a tug of war going here between more assumptions and more data. You can sort of think about this in our category 1 stocks, where we're hoping more data, more information can get into it, versus our category 3 stocks, which are lighter on data and definitely have a heavy reliance on the assumptions we are making. This might be a good time to also to remind us that we have different types of assessments, not just the different categories of assessments, which are kind of based on the data and how we set the model up, but we also have our benchmark or full assessments, where the modeler has a kind of an open freedom to model however they would like. We have our updates, where we rely on the model structure from the previous time, but put more data into it and have a little bit of leeway to do stuff. And then we have our catch-only updates, where we're just putting in catches and basically taking the previous version of the model and pushing it forward. So we have a variety of different types, model type, different ways in which we will be using information, and our stock assessment prioritization often helps us figure out what we're going to do and how we're going to apply, how many benchmarks or full assessments we can do versus catch onlys versus maybe category 1, 2, or 3 assessments. Okay, so now let's get into what is going into the stock assessment. Our data types, the main data types we have are our removals, indices of abundance, and our biological compositions. So let's talk about these in turn. And what I want to point out to you is that when these are going into the assessment, they're telling us something about this fish population that we want to know. So when we are measuring what I'm calling removals, some people might call them landings, discards, catches, right? We have a lot of terms for these things. When I say removals, I'm saying we are trying to enumerate all of the ways in which fish have been taken out of the population through the fishing process. That's what this is here. And that fishery removal, whether it's landings or dead discards, everything put together, all the different sectors, all of this comes together to give us an idea of what has been taken out through fishing. The rest of the removals out of the population are assumed to be due to natural causes, which we'll talk about here in the parameter section. But when we are able to put together a history of removals, we start to piece together how many fish are out there. So this is what we call scale, and the scale or the abundance of the population is really helped when we have a removal time series. If this is highly uncertain, that can make our scale more uncertain. And obviously, when we have a removal time series, it's telling us something about fishing mortality as well. When we add two removals, say an index of abundance or several indices of abundance, what we're hoping that that information is going to tell us is some sort of trend at minimum in the population. Is it going up? Is it going down? And then maybe even how is it going up and down? That how it's going up or down might be indicative of a recruitment time series or something going on in the population. And ultimately, what we would love for it to tell us is kind of where have we landed. And when I say where have we landed, what I mean by that is relative to, say, when the population was relatively unfished, how much has the population reduced down to that? That stock status is an extraordinarily important part of our process of reporting an output from stock assessment. And sometimes our indices of abundance can help us figure out what that is. And at times, these indices of abundance may even tell us something about how many fish are out there. The next set of really important data are our length compositions. They're important because they are one of our easier to access data points. We go out there and we measure fish, and what's interesting about that is that if you can measure fish and figure out how many big ones versus small ones there are, it can tell you something about your stock status, the health of your population. It also very importantly tells us often about our selectivity. We're going to talk about that more in the parameter section, but our selectivity is how we are removing fish through the fishing activity in the population. Knowing what selectivity is a critical part of any stock assessment. So our length compositions can really help us figure out what that is. Length compositions can also help us measure fishing mortality. They can also pick up on a bunch of small fish coming into the population, so tell us something about recruitment. And with the addition to maybe ages, they can tell us something about growth. That brings us to our last major bit of data that we would love to have, which is age compositions. Very, very important information if we can get it. It has a ton of information. And similarly, it can tell us something about the stock status. If we used to have a bunch of very old individuals and now they're all gone, that is indicative of a population that may have truncation and therefore has a lower stock status than it did before. It can also tell us something about natural and fishing mortality. Recruitment, if we get a bunch of young individuals all of a sudden in the population, we see those, that's a good sign that there's a recruitment coming through. It can help us pin down how fish grow over time, and that's a very important thing to track biomass for setting catch limits. And then sometimes it can help us with selectivity. Often our selectivities are set as length based selectivity, but we do have assessments that use age-based selectivity, and so ages would be really helpful in defining that selectivity. Okay, so data are very important. We would like to have as much of it as possible, but we don't just want a bunch of numbers and try to shove them into our assessment. We want them to be quality. And this idea of the data representing or measuring something that we care about is really, really important. And so when we think about how representative our data are they measuring what we care about? We can think about ways in which they cover the different things that we care about. So we can think about time, we can think of space. Are we sampling across all the different areas? Are we covering all the fleets? Different stocks within an area, and are male and females being identified or not. These are all dimensions in which we are trying to collect data, and we would like to have a good representative sample. When that representativeness fails and the data are non-representative, this can create a major source of uncertainty in our stock assessment, and it can even lead to conflicting data signals, which the stock assessor will have to figure out how to deal with. Which data do you believe over the other one, because they're telling you two different things? And so understanding the nature of our data and how representative they are is very important. And so we always ask ourselves, as we're putting something in, just because we have some numbers, if we're going to put them into the assessment, we want them to tell us something that we think is useful, not just go in there and kind of mess things up. So we ask ourselves, how representative are our data? Okay, so if we follow, sorry, I don't have a pointer apparently. But if we follow the line from data into the model, we also see that data can inform us to our parameters. And what are parameters? Parameters are these elements of setting up the model itself. So the model is following how things die and how things grow. The parameters in the model are telling us how things are dying and how things are growing. And so as an example here below the parameter section, we have things called like natural mortality, how things naturally die, age and growth, how they grow over time, reproduction, when they mature, how much spawning potential they have, and lastly, non-biological, but extremely important, that selectivity again. How is the fishery removing individuals from the population? Those parameters are part of what make up the model. And sometimes we estimate parameters and sometimes we don't. We would love to be able to estimate as many parameters as possible in the model, because it helps us use all of the data and kind of push forward all of the uncertainty that we might have. But we often find that we are limited in our ability to always estimate every single parameter. And so you will hear us use the words pre-specify or fix. So if we are fixing a parameter, we are saying, you know what, we are making an assumption. We're going to say we know what it is, and this is what it is, and we're going to run that model. And let's keep that in mind. Anytime we make an assumption, we are going to want to make sure that we explore what if we got that assumption wrong. So anytime we fix a parameter, we usually will go back into the model and fix it to different values and see how much it changes the outputs. And we'll get to that sort of sensitivity analysis here a little later. But those are some of the bigger parameters. Some of the bigger parameters that help that really affect our stock assessment. Natural mortality is one that has a fairly large effect. And another one that I know some of you had a question about was steepness. And steepness is something we'll talk about here in a second. I just want to make sure we talked about fixed versus estimated parameters. I really want you to also feel comfortable when we use the word model specification. All we're talking about is how we're setting up the model and what the shape of some of our assumptions are. So whether it's a stock recruitment curve, we use the Beverton-Holt stock recruitment relationship. It has a certain shape and assumption over time of how the stock biomass relates to how many recruits are created. Another example is selectivity. Oftentimes it can be S-shaped, and we call those functional forms. What's the functional form? What's the shape of our assumptions of some of these parameters and relationships? So that's how we kind of talk about parameters in our model. But this one called steepness is really important because it's trying to tell us how much capacity a particular stock has to create more recruits even when it gets reduced. And so you can see here that if you follow the rainbow colors here, something that has a steepness or an H value of 0.3 has a very low ability to create new recruits over time. It's just barely replacing itself. Whereas something that has more of a stronger hump is getting to the higher recruitment at lower spawning output size. And so this steepness has a value, has numerically for a Beverton-Holt can be between 0.2 and 1. 1 means you can knock the population down to say 20% and it can still create recruitments like it was an unfished population. So very productive. Things that are lower, near say 0.3, are just barely able to replace themselves. You will often see that our ground fishes are somewhere around 0.72, 0.8, something like that. So intermediate productivity for steepness. But this one has a lot of effect in the model. And one thing it does, this is a yield curve. You will see this in our stock assessments. We report this. And what this is telling us is where is that highest amount of yield available at what stock status or relative stock size. So if you are at 100% stock size, that means you're unfished. If you're at 0, you're extinct. And that's what you see here down on the bottom axis. Let's see if I can get a pointer here. You seeing that? Okay, here we go. Great. All right, so here is unfished. Here is extinct. And if we follow these curves, we will see that something that is here is peaking its yield just below 60% of unfished. That has a lower steepness value, so it's less productive than something that you can knock down to below 20% and get the maximum yield. So you can move these yield curves from left to right depending on how you change steepness. There might be someone's mic on. I'm hearing some pounding noises. Okay. So that was steepness. Very important thing. We do often fix steepness or pre-specify it for our groundfish because for rockfishes, we assume it is 0.72, but we will look at uncertainty around that assumption in our models. Okay, so now that we've defined the types of data that we have, the fact that we would like it to be useful, informative, and representative, and that there are parameters that make up the model, and where we get those values, sometimes we get them by estimating the parameter values. Sometimes we have to guess what they are or fix them or pre-specify them in the model. Once all of that's done, we run these models. We do a lot of diagnostics, a lot of things we won't go through here, but we eventually come to a model that we think is trading off the fit to the data, that it's making sense, and giving us diagnostics that look good. This is where we kind of come up with our base or reference model that we can then declare where we think the stock status is and where we can build catch limits from. But before we get to moving on to where we get our catch limits, I do want to suggest to you that not only stock assessments are very complicated, but you can boil them down. And this is particularly useful if you use these three terms here to look even across assessments and ask yourself, why has an assessment changed its perception of the stock from one to the next? So we've talked about all of these, but I want to make sure we understand them well. The idea of scale, or how many fish are out there, conceptually easy to understand, but you can follow how has scale changed across assessments. You can also follow how stock status has changed, and what stock status is, again, how many fish are left relative to the unfished. 65%, 40%, 25%, those sorts of things. We report those routinely, and they're part of our control rules, and this is the metric by which we measure whether the fish is overfished or not. And then lastly, productivity is at birth minus death plus the growth of individuals that are left. Basically, the rate of new numbers of biomass. How productive is the stock? If you change the productivity, say you change the steepness from one assessment to the next, you should be prepared to see a different scale and or stock status just by changing the productivity. So by changing any one of these three or all three in a stock assessment, we're going to get different results. But most of the complexities of stock assessment can be boiled down to what is it doing to scale, what is it doing to status, and how has productivity changed from one assessment to the other? Okay, so once we've gone from data and parameters into the stock assessment, into the output, and I've put down here a reminder to you that you should, when you are looking at output, especially from assessment to assessment, you should be looking at how these things have changed. We now enter the reference point and control rule part. How are we actually interpreting stock assessment? Many of you have been doing this for a long time, and you know this very well, that we have a proportional threshold rule called the 40-10 that says, and I'm going to use one of our rockfish examples here, that we are targeting. So we have a target reference point. So a reference point is, what are our objectives? Where do we want to be? We want to be at 40% of unfished. So we want to reduce the stock by 60%, essentially, is what we're saying. So we're targeting this, and anything above this, we will have this one line that reduces our catch until we get to 40%. Or our catch will be along this line until we get to 40%. Once we drop below 40%, though, we are going to have a different angle of a reduction. It's going to be a faster reduction, and that line goes from 40% down to 10%, where in which we would theoretically have no more catch. But we all know as well that our limit reference point for rockfish is 25%, and if we fall below this, we become we break out of this control rule and we go into a rebuilding plan. So this is our limit reference point. We don't want to go below the limit reference point. We would like to be here. So these are our typical reference points for the 40-10 rule. But then we have this idea of, okay, this is what we're setting our catch limit by, but that's not the only thing we use. And I'm sure many of you have run into the P-star and the P-star approach. What in the world is this? Many of you may already know this pretty well, but let's just go through it really quickly. P-star is essentially the probability of overfishing. Out of our stock assessments, we get some sort of distribution of OFL, overfishing limit, right? And so we get this distribution. Oftentimes it has a longer tail. It's called a log normal distribution. So you will see it's not totally bell-shaped. It will have a longer tail. But the most important part is that there's a thing called the median, which is the middle part where there are the equal number of catches above and below that number. So I have rigged up a situation where we have an OFL median of 500. And the overfishing limit comes from the stock assessment. The ABC, acceptable biological catch, comes from the SSC. And the annual catch limit will come from the council discussion. And we have ACTs and harvest guidelines and other things. But let's talk about where this is coming from here. So this ABC is going to be coming from out of the stock assessment. We not only have this distribution and this this middle value of an OFL, we will call this middle value the risk neutral. We have the same amount of values above and below it. But the P star is allowing us to say we want to be precautionary. We don't want to maximize our probability of overfishing. So we want to stay away from the OFL a little bit. And that's why this whole system was designed. How can we buffer or move away from the overfishing limit? The way that we do this is that we have two things. We have the variance that's coming out of the stock assessment. We call that sigma. And in this case, it's a sigma of 0.5 that we're going to use to set this. But we also have the P star value itself. The P star value itself is the percentile of this distribution that we want to pull the catch from. So in this case, we have one distribution, and we're going to look at different probabilities. So P star of 0.5, that is the middle. That is the 50% above and below. A P star of 0.4, this lowest one, means you have 40% below this and 60% above this. We typically use a 0.45 to start with. That's what the SSE is typically using, is a 0.45 along with some sigma value to figure out how far away you could buffer this. Now, one thing I want to point out to you is that if someone were to choose 0.499, 0.4999 is essentially 0.5. You can't see the 0.5 here because it's covered by the 0.4999. If you chose a P star of 0.4999, what you are essentially saying is we don't care about the uncertainty of the stock assessment because we're basically nullifying it. The uncertainty in the stock assessment really starts to come out when you have something much less than that. So 0.45, we can start to see a difference. So instead of the OFL is 500, if we used a P star of 0.45 and a sigma of 0.5, we would get basically 470 metric tons instead of 500 metric tons as our ABC. Now, different stock assessments have different levels of uncertainty or sigma. And so if we show this, here's one where they all have the exact same median value of 500 metric tons. But this one has a sigma of 2, this one has a sigma 1, and this one has a sigma of 0.5. You can see that this is much more spread out than this one, which means when you take the same percentile, 0.45 P star, that's the same percentile as this one, but because it's so much wider, it gets pushed over farther, and that is why our category 3 stocks that use a sigma of 2 are going to have a much larger reduction than our category 1 stocks that have a sigma of 0.5 for any given similar P star. So the combination of P star and the width of the uncertainty that you're assuming in the OFL distribution will tell us what our ABC is. All right, lastly, to wrap this up and get some more questions here, our control rules go into management measures. Lynn, Keely, obviously this is more complex, and you all have been telling folks here how to define all that stuff. I'm not going to get into the discussions of what qualifies as a management measure, but just suffice it to say we can control catch, we can control effort. This is just basic fisheries management type stuff when I say management measures. But our control rules are going to usually trigger some sort of catch setting or something, and we go from there. Lastly, I want to finish up on uncertainty. As I said, our models, we don't claim to know everything, and in fact, that's the opposite. We claim to do our best to characterize uncertainty. Here, if this is the model uncertainty, here are all the contributions to model uncertainty. We talked about data representativeness. If our data are a little bit wonky, that can create some problems. They might just be straight up just not really informative. Our parameters, whether we estimate or fix them, natural variability, just recruitment variability and growth variability, these things can create just uncertainty in the model. How we assume we're setting our model up, what functional forms we're using can create uncertainty, and the type of model. Are we using a really, really simple model? Are we using a really complex model? The type of abstraction that we're assuming, all of this contributes to uncertainty, and uncertainty we often articulate in bias and imprecision. And from bias and imprecision, we get some sort of ability to interpret. How do we interpret that uncertainty, right? We have some level of unpredictability and some level of risk. And we've talked about the P-star approach, trying to quantify how we want to approach our risk decisions. Now, back to those terms of bias and precision, what we would like to be is unbiased, meaning we are accurately hitting the target and we do it every time. We have very precise estimates of all of our parameters, great informative data. This is where we would love to be. Very rarely are we there. And when we aren't there, sometimes we can be fairly unbiased, but have a lot of uncertainty around that. There's other times where you can have a low uncertainty, but be highly biased. This could happen, for instance, if you fix a bunch of parameters, but you fix them to the wrong value and you didn't know they were wrong, you could be, and you come out with a very low uncertainty in your stock assessment, but you have a high bias. And then lastly, where we really would not like to be is both biased and imprecise. But this is how we express our understanding of uncertainty. So when we talk to each other about uncertainty, we should use the terms bias and imprecision to help us understand what we're really talking about. Okay, so a couple of things to finish up here, and then I will take us into looking at uncertainty, how we quantify uncertainty in our stock assessments, and then we can get some questions. Okay, so stock scale, how many fish are out there, can be very uncertain. And it's oftentimes one of the more uncertain things in our stock assessments. It's just hard to count how many fish are out in the ocean. And so you might see scale fluctuate from assessment to assessment. That's not going to be a surprise. We do our best to count how many fish are out there, and that scale can change a lot. Even if the stock status doesn't change, the scale can still move around. That leads us to an observation that we do tend to be a bit better with our stock status. It tends to be a little less uncertain than scale often, but it can also be large. And one thing that we can notice is that even if we don't know the scale, we can actually get stock status, and we can do this without even having catches. We can just use length or ages to give us an idea of what the scale is. We just won't be able to, what the status is, but we won't know what the scale is, and therefore we can't set catches. So that's no good. When we focus on just one base model, we are likely underestimating uncertainty because one model is just one realization of a model specification. And so you will notice that in our stock assessments, we do lots of different model runs, and we also do high and low states of nature for our decision tables. We try to work hard to put together many different models to demonstrate where our one reference model might be underestimating uncertainty. And so that underestimation comes from us just fixing parameter values and just missing other model specifications, right? Just doing it wrong. And so we really work hard to look at a lot of different possible models to understand where that uncertainty might come from. And more data does not mean more information. We need to see contrast. We need to see, what I mean by contrast is differences in the trend of the population over time, in the mean lengths of the animals over time. If we don't see those things, it's really hard to understand what is going on. So a flat time series may not tell us much, even if we have a lot of data. That can be very frustrating. All right, so I think I'm finishing up on this. When we explore uncertainty in stock assessments, we do several things. One of the most important things we do is play around with the assumptions in the model. What if we changed steepness? What if we changed natural mortality? What if we estimated this one parameter instead of fixed it? What if the length at maturity was this value instead of this value. So we do a lot of different explorations. And you can see here, if you can see the shadow around this line here, that's the one model estimation of uncertainty. But you can see here that these other model explorations expose a bit more uncertainty than just the one model. We also do what's called a retrospective, which we peel back values in time to see if we can kind of get a consistent trend and scale. And if we don't, we might ask ourselves, have we messed up setting up our model? Because all of a sudden it switches to a different behavior once we start removing a datum point or two or whatever. So that the retrospectives you will see us do. Likelihood profiles, this is a way in which we look over a whole bunch of values. Say natural mortality, we start from a low value and say we look at 12 different values up to a higher value, and we see how important outputs of the model change. And that helps us inform how much the model knows about that parameter and how sensitive it is to that parameter. And then lastly, after doing all of these things, we often will identify kind of the most important, what we call axes or sources of uncertainty. And we put together a low and a high version. Say in this case, we used low natural mortality values, high natural mortality values. This is a more productive stock. This is a less productive stock. And this is our reference or base model. And that helps us bracket the most important places of uncertainty. And then we can run models forward under that uncertainty under different catch scenarios to tell us what might happen. It's just another way of looking at the risk of getting it wrong in the stock assessment. Okay, we are just under time. I know we started a little tiny bit late. If there are some questions, I would love to take them.